people on Zoom can see the 4 images that I was talking about. And I will start with an introduction and back to basics so that everybody's on the same page. There are 3 fundamental processes that lead to gamma ray production in astrophysical environments that are particle decays, particle annihilation, and nuclear decays. And then there is a broad class of phenomena that involve particle acceleration and interactions that lead to gamma ray production. We can differentiate between hadronic processes that proceed to production and decay of unstable particles like pi zeros, and then there is a number of leptonic processes that lead to gamma ray production through interactions of leptons with interstellar radiation fields, matter, and magnetic fields. And these different gamma ray production processes are actually what sets the scientific scope of gamma ray astronomy. Due to the fact that gamma ray production happens in this way, it means that through gamma ray observations, we can observe a set of phenomena that I grouped in this slide in 4 broad classes that are the origin and interaction of cosmic rays, physical processes in extreme environments, physics beyond the standard model, and the formation of heavy elements. For the crowd that is gathering here and my personal interest, I will be focusing most on the first 2 topics. But for the third one, that is probing physics beyond the standard model, there were already a number of talks, including the review by Gabi yesterday on dark matter searches with astrophysical probes. The other key ingredient, of course, is that we need to detect gamma rays, and gamma ray detection is performed using a number of different techniques. The Earth's atmosphere, as you well know, is opaque to gamma rays. So a chief principle for gamma ray astronomy is using balloon and space-based instruments. These instruments use different detection techniques depending on the gamma ray energy, because depending on the gamma ray energy, the main interaction processes of gamma rays with matter vary. The challenge here is that in the energy range above 100 keV, roughly speaking, it's impossible to focus radiation. So you need a detection technique that enables you to get directional information without focusing. This is the specificity of gamma ray astronomy, if you want. At the lowest energies, below MeV, the main interaction process is the photoelectric effect, and the instruments that we use now are based on coded masks that enable us to get directional information from the shadow that the coded mask casts on the detector. The state-of-the-art instrument in this case is represented by Integral, which is operating since 2002. Around the MeV, the main interaction process becomes Compton scattering. So we can do gamma ray astronomy by exploiting the kinematics of Compton scattering. In this case, the state-of-the-art is represented by an instrument, COMTEL, that was flying between 91 and 2000. And recently there have only been balloon experiments. By the way, these are called the low energy and medium energy gamma ray bands often. And then the high energy band above tens of MeV, where the main interaction process become pair production. And in this case, we use pair production telescopes that use the kinematics of pair production to determine direction, coupled with calorimeters for energy measurement. The kind of state-of-the-art instrument in this case is the Fermi Large Area Telescope, taking data since 2008. There are a few other existing instruments like Agile and DAMPI and CALET. These latter 2 in particular are multi-purpose instruments, but they also have interesting capabilities for gamma rays, in particular very good energy resolution. The satellite measurements do not manage today to reach beyond TeV for technological limitations, essentially size limitations for space instruments that, coupled with the rapidly decreasing gamma ray fluxes with energy and the necessity to contain the gamma ray shower to a good extent in order to be able to perform a calorimetric energy measurement, make it impossible to reach the highest energies. So at the highest energies, as you know, we use ground-based instruments. This was already covered in detail in the talks by Petra and Alison on Monday. There will be some overlap, of course, but you already heard on Monday that the principle is detecting the products of gamma ray interactions with the Earth's atmosphere. There are two main families of solutions that are adopted, either studying the chunk of light from the particles in the shower. This is the technique used in atmospheric Cherenkov telescope arrays. We call this traditionally the very high energy range, and the three main instruments operating today are HESS, Veritas, and MAGIC. The other possible solution is to have some sort of particle detector that directly samples the particles in the shower. The main instruments operating today are HAWC, LASO, and Tibet. And these cover the energy range from the very high energy to the ultra high energies. And as you heard on Monday, these two different techniques are very complementary, because on one hand, we had a better PSF, but a modest field of view and a low duty cycle. On the other hand, we have a modest PSF, but a large field of view and a high duty cycle. So now that the basics have been covered, I will give you a general overview of recent results in gamma ray astronomy. And I will start with this general overview, talking about sources. The sky map shows the sources in the most recent 12-year Fermilab catalog, so in the high energy range. And you can see that there are a number of different classes of sources that appear on this diagram, including AGNs, supernova remnants, pulsar wind nebulae, pulsars, binary systems, and many others that you can read here, including unassociated sources. And one important point is that there are no gamma ray bursts here, but it's just because gamma ray bursts are not included in the general Fermi catalogs that are based on detection on long time scales, but Fermi already detected more than 186 GRPs. Now, if we switch to the very high energy domain with sources detected by ground-based instruments, you see that, well, we have fewer sources to start with. You see that AGNs are still dominating in the extragalactic sky as the main source class. On the galactic plane, the panorama changes because now the main classes of sources appearing are supernova remnants and pulsar wind nebulae and halo. But there are also a number of other source classes that were detected. And we can summarize this using these pie charts, where you can see the features that I've already been talking about. You can appreciate how many unassociated sources there are still in both energy ranges. And the most important aspect to be discussed about this plot, in my view, is the fact that nowadays we have a large number of sources, different classes of sources in gamma ray astronomy. And this is very interesting because they make it possible to learn about particle acceleration in a variety of astrophysical environments and conditions. And for the main source classes, we have populations of sources, which means that even within one single source class, we can study how things change for different conditions, environments, ages. This is what I called the coming of age of gamma ray astronomy in the title of the talk, because at the beginning, gamma ray astronomy was born as a branch of cosmic ray science, more or less, to look for cosmic ray sources and to study some extreme objects. But nowadays, we are really at the point where gamma ray astronomy is a fully fledged astronomical discipline. I wanted also to highlight the number of sources. This was already shown a bit by Alison, I think, on Monday. So you see that there is a progression on the number of high energy sources that, funnily enough, looks almost exponential on this plot, with more than 6,000 sources in the most recent Fermi catalog. Here you have the cumulative number of sources detected by ground-based gamma-ray instruments. In particular, I wanted to highlight the change of slope coincident with the beginning of operations of HESS, MAGIC, and Veritas, and the jumps that correspond to the publication of the second HAWC catalog and the first results by LASO. For completeness, I wanted to mention that there are only 63 sources in the COMTEL catalog, so in the MeV energy range, while if we go below 100 keV, Integral HIBIS detected almost 1,000 sources. Now, there are not only sources in the gamma-ray sky, there is also diffuse emission, which is emission not associated with individual sources. And I wanted to start by showing this plot that compares a gamma-ray image taken by Fermi-LAT in the region of the anti-center, the Taurus and Perseus molecular clouds. In this image, individual sources and smooth backgrounds were already subtracted, and you can compare this with the dust opacity as inferred from Planck data. And you can see that there is really a striking similarity between the two. This is something that has been known for a while, of course, even though the recent images have a much higher quality. And this testifies basically that most of the diffuse emission not associated with sources in the GeV energy range is actually probably produced by cosmic ray interactions with interstellar matter, which is why we can use it to study cosmic ray transport and also to understand the origin of cosmic rays. Now, in recent years, the energy range where we do detect diffuse gamma ray emission has been extended, and it goes basically from below MeV to PeV. In particular, I wanted to highlight these recent results. You see that thanks to Tibet and LASO, now the spectrum of diffuse emission can extend much beyond what Fermi can measure, up to PeV energies. However, there is one key question that needs to be addressed when you study diffuse emission with gamma ray telescopes, which is still very much open in my opinion, which is the emission that we see due to cosmic ray interactions or to unresolved sources? Because the sensitivity of the instruments is limited, and so it's almost guaranteed that there are some sources that are not individually detected and are therefore seen as diffuse emission. As I explained, at GeV energies, the good correlation with interstellar matter tracers testifies that probably the bulk of the emission comes from cosmic ray interactions. But the situation becomes much less clear when you go to lower or higher energies. In the MeV and sub-MeV energy range, as you can see in this plot, there was the detection of diffuse emission with Integral. It was initially interpreted possibly as the result of positron annihilation and cosmic ray inverse Compton scattering. However, recent studies that take into account AMS results and synchrotron measurements conclude that the observed emission is about 3 times larger than what you expect based on inverse Compton scattering. Although a significant contribution from secondary positrons and electrons can, from this plot, reproduce the observations, actually this seems to be in tension with other kinds of measurements. So there is an alternative explanation that probably makes sense investigated and seems even more likely. That is that this diffuse emission in the sub-MeV energy range has a sizable contribution from unresolved sources that have not been pinned down yet. The same thing goes for the TeV TeV to PeV diffuse emission that I showed the spectrum of in the previous slide. This is very interesting because in principle it connects with the possibility that the cosmic ray spectra are harder in the inner galaxy that was suggested by Fermi. But today, in my opinion, we still need to conclusively evaluate the contribution from unresolved sources, and there are a number of works being done recently on this. Here I took just an example of a population synthesis models for pulsar-wind nebulae, which are the dominant source class in the galactic plane at TeV energy, and you see that below the sensitivity limit of the current experiments, that is basically here, we expect a large number of sources that therefore will be contributing in current measurements to diffuse emission. Now, this concludes the general overview. I wanted to give you some concrete examples of how the recent measurements are really making it possible for us to understand particle acceleration and transport in some different environments, but I won't have time to cover all the different objects that are nowadays observed by gamma ray instruments, so I decided to focus on a few examples that are particularly interesting in my opinion, and I will start with pulsar halos. Pulsar halos are a class of objects that was only recently discovered. This started with observations by Hawke of extending the halos of gamma ray emission around Geminga and pulsar BO656, also known as monogamma. You can see the radial profile measured by Hawke as a function of radius or distance from the pulsar for Geminga in this plot. You see that the emission extends up to 15-20 parsec from Geminga, and the interpretation that was made was that we are seeing particles that are free from the pulsar-wind nebula, and diffuse around the source. But in order to explain the radial profile seen by Hawke, one needs to assume that the diffusion is suppressed by a factor of 100, roughly speaking, with respect to what is inferred from the elemental abundances like boron over carbon. There was another interpretation that was put forward later for these observations. That is, so the interpretation based on the suppressed diffusion is the orange curve here. The second interpretation that was put forward later invokes a combination of ballistic propagation close to the pulsar itself and then average diffusion, and this is the blue curve. However, you see that it does not reproduce the data as well as the orange curve, and on top of that, this kind of interpretation still requires to better understand the ballistic propagation in the magnetic fields near the pulsar. So I would say that the interpretation with suppressed diffusion is still favored as far as I understand. And after these first discoveries, there were a few more objects that could be halos that were detected at TeV energies, although some of them may be transitional objects between pulsar-wind nebulae and halos. And there was also a tentative detection of the Geminga halo with Fermi. In general, the interpretation of what is happening is illustrated in this plot here, where you see that a pulsar-wind nebulae system goes through different steps in the evolution. At the beginning, the pulsar-wind nebula develops inside the supernova remnant. Then at some point, the supernova remnant reverse shock crashes the pulsar-wind nebula. We have this intermediate step, and finally, somehow the pulsar-wind nebula, after the pulsar exits the supernova remnant, develops as a bow shock, but there is propagation with diffusion forming a halo for middle-aged and old pulsars. The key questions, however, to be addressed for this new phenomenon are the following. How is the suppression of the diffusion coefficient realized? What is the physics behind that? And how many of these objects do we have in the galaxy that could be detected by future instruments or contribute to diffuse emission? So for the suppression of the diffusion coefficient, there was a number of theoretical attempts to reproduce it, invoking additional turbulence that can be of kinetic or fluid origin. And also there was discussion about reduced turbulence coherence length. I took as an example here a plot from a paper by Carmelo, where the turbulence of kinetic origin was shown to reduce the diffusion coefficient with respect to the galactic average, but by a couple of orders of magnitude only for a relatively short time. The contribution to source populations and diffuse emission is still an open question. I wanted just to point out that this is related to another issue that was brought up several times here, that is the origin of the positron excess. And we have shown in a recent paper that based on a simple two-zone diffusion model, if you assume that all the nearby middle-aged pulsars produce halos in a way similar to Geminga and monogam, you would probably exceed the positron flux measured by AMS. This, however, needs to be requires further work because it's based only on a few samples of nearby objects. The second class of gamma ray emitters that I wanted to cover with a bit more details are star-forming regions. Star-forming regions, on the contrary, were expected gamma ray emitters since the 80s for a combination of different reasons. On one hand, star-forming regions host many different classes of potential particle accelerators and provide good conditions for particle acceleration. They have large reservoirs of matter and radiation fields that act as a target for gamma ray production. And on top of that, the cosmic ray isotopic abundances like neon and elements around iron suggest that a fraction of the cosmic ray fluxes, around 20%, may actually be sourced from the winds of Wolf-Rayet stars. The detection, however, in gamma rays was only reached during the last decade, basically, and now there are more than 10 star-forming regions possibly detected at the GeV and TeV energies. In this case, however, there is a caveat. Gamma ray telescopes still have a limited angular resolution, and star-forming regions are affected by large foregrounds and backgrounds because they are in the galactic plane. And on top of that, there is a clustering of different sources in these star-forming regions. So it's often difficult to conclude whether the gamma ray signal we see is related to the star-forming region as a whole, or it is something related to a few objects residing in the star-forming region itself. In my view, but I'm certainly biased here, what remains the best example where we are relatively sure that what we see is related to the star-forming region is Cygnus, because in this case, the gamma ray signal is clearly correlated with the cavities that are carved in the interstellar medium by the star-forming activity. We can see the borders of in this infrared image on the right here. So you see that there is a very good correspondence. For the most remarkable objects, the radial profile of cosmic ray densities was inferred from gamma ray observations, and you can see that it scales approximately as 1 over the distance, and this was interpreted as the signature of continuous cosmic ray injection plus diffusion over a few million years. The nice thing is that these observational developments have now stimulated a lot of modeling. So contrarily to 10 years ago when I started working myself on this topic, now we dispose of models that predict what the signal from acceleration in star-forming regions should look like, and enables us to make comparison with the observations. There are different possible acceleration sites and mechanisms that have been studied, including cluster wind termination shocks, super bubbles and super shells, and converging flows. The latest results indicate that the acceleration of particles seems to be feasible up to PeV for clusters. This is much less clear for superbubbles. And I put here some plots from a recent paper that model cosmic ray acceleration and gamma ray emission from superbubbles. It's interesting to see in the upper plot that if you look at the total energy of cosmic rays as a function of time, you see that there is a phase of steady cosmic ray production in the early phases where the mechanical energy is dominated by stellar winds, and then the cosmic ray production and therefore the gamma ray emission may become intermittent when you are dominated by supernova explosions. On the bottom you see a gamma ray spectrum for one of these example star-forming regions as a function of age from 1 megayear to 20 megayear, and you see that for a few megayears you get a good reproduction of the spectrum measured for Cygnus. This is not a fit, this is just a model compared to the data. And sorry, I went back too fast. This is obtained when you have good confinement in the shell, which is also important because this, as for pulsar halos, point to some longer residence times of cosmic rays around their sources, potentially, and this may have an impact to understand the life cycle of cosmic rays in the galaxy. My final example for a specific class of objects is gamma ray bursts, for which we recently detected very high energy gamma ray emission. This was looked for a long time, and the emission from GRB afterglows is especially interesting because they represent particle acceleration in relativistic shock in its simplest realization. And the general expectation was that this would be due to synchrotron self-compton, because you cannot reach very easily very high energies with synchrotron emission due to the synchrotron burn-off. So to the limit on the maximum particle energies that is set by synchrotron energy losses. So recently there were a few detections, 4 well-established, possibly a couple more. Here you have the light curves for 2 remarkable objects detected by MAGIC and by HESS. And what is interesting to see is that in one case, MAGIC detected emission from the early afterglow phase, basically around 60 seconds after the trigger, while in this case it's a later detection. But in both cases there is a good correlation between the temporal evolution for gamma rays and X-rays. I wanted to tell a few words more about one of these 2 GRBs, 1908-29. It's one that gave the most interesting results in terms of physics because it was at very low redshift, and so there are fewer uncertainties due to EBL absorption. Here's the plot from the original HESS publication, where they showed that the spectrum at TeV energies is not well consistent with the synchrotron self-Compton scenario that is shown in blue. So they speculated that this may be synchrotron emission above the burn-off limit. But a more recent paper has shown that actually you can build a consistent synchrotron self-Compton scenarios if you combine a few percent of accelerated electrons plus rapid decay of magnetic field in the reverse shock, and in this case you can reproduce the data from radio up to TeV. But there are also other alternative explanations that are explored in the literature. So this concludes the part that I called the coming of age of gamma ray astronomy. In the second to last part of my talk, I wanted actually to talk about 2 recent developments that, from my point of view, really change the way that we do science with gamma rays, and that's why I call them revolutions in the title of the talk. The first one is the advent of multi-messenger astronomy with gamma rays. You know that in recent years, we had the first detections of gamma ray and gravitational wave emission from a source. That was gravitational wave 170817. And then there was this first association between a neutrino detected by IceCube and the flare in a blazar detected by Fermilab and MAGIC. Now, the significance of the association between the two is challenged by some recent analysis. The significance may not be very high, but anyway, this spurred a lot of interesting joint studies of gamma rays and neutrinos. And I use this cartoon here to illustrate why I think that it's really a game changer, these multi-messenger observations, because indeed as astronomers, we are a bit like the blindfolded men that are touching the bits of the elephant. But if we put together the information from all of us studying gamma rays, neutrinos, and gravitational waves, we'll certainly have a much better insight on the physics that is behind our observations. For neutrinos, we had already the overview talk by Fotini yesterday, so I won't say anything more, but I wanted to give at least one example for the joint gravitational wave and gamma ray observations, of course, 170817, just to illustrate how powerful to understand the physics at play in this object were the joint observations in gamma rays and gravitational waves. So what was obtained by these observations was that the fractional difference between the speed of gravitational waves and photons was constrained to be in this 10 to the minus 15, 10 to the minus 16 range. There was an improvement of a few to a 10 on minimal Lorentz invariance violation scenarios. The comparable duration of the decay time for the gamma ray signal and the delay between gravitational waves and gamma ray signal constrained the emission mechanisms for gamma rays to be either an internal shock with small difference in the shell's Lorentz factor or an external shock with Lorentz factor around 300. There were constraints on the neutron star mother equation of state. Here you have a plane with the masses of the progenitors inferred from the gravitational wave signal. And you see that based on the gamma ray observations, there were constraints on the relation between the two that were the strongest ever obtained in a part of the parameter space. And finally, the dimness of the GRB compared to the masses inferred from the gravitational waves made it possible to put constraints on the engine structure or end viewing geometry that are illustrated here. So, second revolution, from my point of view, is the opening of the PeV frontier that happened very recently with instruments like LASO, HAWK, and Tibet. Why is this important? This is tied to a classic problem in gamma ray astronomy, that is the hunt for pevatrons, that is the accelerators that must be able to accelerate in our galaxies particles up to the knee of the cosmic ray spectrum, so energies around 1 PeV. This is something that is actually difficult to do, and supernova remnants that have been for a long time the main suspects for the accelerators of galactic cosmic rays are challenged as pevatrons, both from the point of view of observations, because typical observations of supernova remnants in gamma rays show steep spectra and cutoffs well below PeV. And also theoretical models of particle acceleration in supernova remnants show that for the most common classes of supernova remnants, type 1a and 2, actually it's very difficult to reach PeV energies. And only some rare classes of supernova remnants perhaps can reach these energies, but for a short amount of time. What was generally believed until recent years was that leptonic accelerators cannot produce effectively gamma rays above 100 TeV due to Klein-Nishina suppression, and therefore if we managed to detect gamma ray sources above 100 TeV, the few sources detected would pinpoint basically the sources of hadronic cosmic rays in the galaxy. Now, you have already seen that the picture changed a lot thanks to HAWK and to LASO that detected an unexpectedly large number of sources above 100 TeV or 50 TeV. There are at least 12, but possibly even more detected by LASO. I wanted to point out the key technological feature that enabled this to be possible, that is the use of underground muon detectors. And the maximum photon energies measured by LASO for the 12 sources span from 200 TeV to 1.4 PeV. There are, however, only few spectral measurements so far, and so it's not clear yet whether these are really hard spectra extended up to PeV, or perhaps we are measuring sources already in the cutoff regime. What is interesting is that this also brought forward new considerations on the origin, meaning are all these sources really accelerators of nuclei? The answer perhaps is no. There are two indications to take into account. If you look at the maximum photon energy for the LASO sources, you realize that most of them are actually close to a pulsar, and the maximum photon energy that you observe is below the maximum limit that is set by the pulsar potential drop. Combine also with synchrotron limits. The only exception where this does not seem to be possible is this source J2032, which is actually coincident with the Cygnus star-forming region. There were also some models, including this one that I'm showing here, that show that actually there are conditions where emission above 100 TeV can be expected even for leptonic processes in the case where particle energy losses are dominated by inverse Compton scattering, and therefore something that could happen, for example, in star-forming regions. Now, this concludes the overview of the results. I wanted to use the last few minutes to highlight future prospects for observations, and I will start by showing this plot that has the sensitivity as a function of energy for continuous emission for the existing instruments that I have been talking about during the talk. And the main feature that I wanted to highlight here is this so-called MEV gap. You see that around the MEV, the sensitivity of the state-of-the-art instruments is actually much, much worse than what happens for the nearby energy ranges below hundreds of keV and at GeV. There are a couple of upcoming instruments that are already funded and on the way that will change the panorama in the next 5 years or so. So there are a few of them in the TeV to multi-TeV energy range, including CTA and the ASTRI Mini Array, and the COSY satellite that will make the first dent in the MEV gap. So a couple of words on this. So COSY is a Compton detector based on germanium cross-tip detectors. The detector itself was already flown on superpressure balloons. For example, here you see a map of the 511 keV positron annihilation line made using the balloon flight. And now this instrument has been approved for a small explorer mission by NASA. So it will be launched in 2025, expected launch date. COSY combines imaging, spectroscopic, and polarimetric capabilities, and therefore will be able to study the origin of positrons in the galaxy, the formation of heavy elements, and polarization in pulsar-wind nebulae, AGNs, and GRBs, which are all breakthrough capabilities. It will make huge advances or first measurements in many of these. And here you see as an example the line sensitivity as a function of energy for the COSY 2-year survey. It improves a lot with respect to integral, and you see that it is sensitive enough to detect the positron annihilation line, of course, but also heavy element lines in many galactic systems. We already heard quite a bit about CTA. I won't say much. I wanted just to point out that in addition to the large sensitivity, that you have already seen in the plot that I have shown. CTA also has many other instrumental capabilities that make it a true multi-purpose, multi-science detector, including large energy range that enables us to do cosmology and pevatron studies at the same time, rapid slewing time to study transients, a relatively good energy resolution, a large field of view that makes it possible to perform surveys, and a few arc-minute angular resolution that enables us to perform detailed morphological studies. And CTA is now in the final preparation phases. Construction is expected to start very shortly, possibly next year, and to last a few years. So to conclude, I wanted to go from the upcoming instruments, so what is more or less guaranteed to happen, to instrument concepts that could further advance our capabilities to observe gamma rays. You see that there are a few in the multi-TeV energy range that we heard about already in this conference, like SWGO and Alpaca. But what I really wanted to point out is that there is a huge margin for progression in the GeV and especially MEV energy range, where there are some instruments that are proposed that either use new technologies to really advance by a lot the observing capabilities. It is the case for Astina with Laue lenses, or for Harpo and APT that do pair tracking with new technologies that are time projection chambers or scintillative fibers. But I also wanted to point out that there are detectors that are based on established technologies that combine multiple detection techniques in a single instrument. So it can be coded masks plus Compton for Gecko, or Compton plus pair tracking for Amigo and Astrogam, and would really already enable a huge progress in the MEV, sub-MEV to GeV energy range, definitely getting over the MEV gap. So I will finish here. Summary of my talk. Now, let's see why it doesn't want me to show the last slide. There does not seem to be a last slide, the one on the MEV gap. Oh, really? There is no last slide? Okay, then there was a problem with the production of the PDF. I apologize. But so the summary of my talk is basically that I think that with the recent observations in gamma rays, gamma ray astronomy definitely progressed from a science that does studies of cosmic ray sources and extreme objects to a fully fledged astronomical discipline that makes it possible to study a variety of astrophysical environments and conditions. There were these two big revolutions that occurred in the past 2 years that were the opening of the PeV frontier and the beginning of multi-messenger astronomy, including gamma rays. And as it is shown by this plot, there is a large margin for progression in gamma ray observations that could open up even more science opportunities. And that's all. Thank you.